Okay, so I tried to make GR comprehensible, and in words, we didn't have the equations that are the meat of the subject available. And the question at this point is, okay, having made all this effort, is it worth it? What do we get for it? And gravitation is what drives astronomy. We know that. So we expect GR to be important in astronomical circumstances. And indeed it is. And the first check of Einstein's theory, performed by Einstein immediately in 1916 when he figured out the general theory, it has to do with the orbit of Mercury. Remember that what we saw was that Newtonian results are with a minus gmm over r potential energy are modified by general relativity, adding this 1 minus v squared over c squared term. And the fastest moving planet in the solar system, of course, is Mercury. And so you might expect to see this effect. And what does this do? Well, any deviation from minus gmm over r will ruin this beautiful property of Kepler orbits, which is that they are closed. In other words, a Keplerian orbit is this red ellipse over here, in which every period the planet returns to exactly the same point, and the orbit is exactly periodic. This is not a property of orbits in general, and indeed it's not a property of Mercury's orbit. Mercury orbits the sun in an ellipse, but that ellipse is precessing like this blue ellipse, so that Mercury does not return after a full orbit to exactly the same point. It actually deviates slightly. Now, the deviation is very slight. This is highly exaggerated. In fact, the deviation had been measured long before Einstein to be about 1.5 degrees per century. So imagine the axis of this blue ellipse rotating 1.5 degrees per century. And most of this is due to what perturbs the pure Newtonian potential in which Mercury orbits. Well, most of the deviation is to do, of course, with the gravitational influences of Jupiter and to smaller extent other planets. And to an even smaller extent, the fact that the sun is not exactly a sphere, it's slightly oblate, it's fat around the middle due to its rotation. All of these effects were in the precinct of Newtonian physics, had been taken into account and tallied carefully, famously by Verrier in 1859, and he came up with a result that was almost 1.5 degrees per century, but was short by 43 arc seconds per century. This gives you a sense of the precision with which the calculations were done. And what Einstein does is he computes the effect of this term on the precession of the perihelion of Mercury, and putting in the parameters for Mercury, he gets exactly 43 arc seconds. And so some part of the failure of Mercury's orbit to be closed is due to general relativistic corrections, and this is the first validated prediction, if you want, the first validation of his theory. Clearly, given this v squared over c squared term, when you have close binary stars like the Algol system, two things with masses of order the mass of the sun, orbiting each other with an orbit that is an eighth of the orbit of Mercury, the velocities are suitably higher, and there general relativistic effects are going to be more important. So whenever we're dealing with orbits and using Newtonian physics, we were making approximations, which we will by and large continue to make, by the way. We will not be doing, but we know now that we were missing something. Since then, precision tests of Einstein's theory have been done in various ways. Famously, I just have to mention this, by the Gravity Probe B mission, which recently finished a measurement of the deviations from Newtonian predictions due to the curved geometry around Earth, as well as the tiny effect of Earth's rotation turns out to change the gravitational behavior in the vicinity of Earth due to general relativistic corrections, and both of those were validated brilliantly by the Gravity Probe B mission. We won't get into too many of the details of this. There's a famous second validation of Einstein's theory. Remember that one of the predictions of general relativity is that gravity acts on light. We found that through the equivalence principle, you can argue rather easily through the mass-energy equivalence that gravity has to have an effect on light. This settles an old dispute. There was always the question, on the one hand, the force applied by gravity is gmm over r squared, and light beam has a vanishing little m, so the force should be zero. On the other hand, the acceleration due to gravity is gm over r squared, and here the little m is gone, and so would light be accelerated in a similar way? Would light or would it not be affected by gravity was an old debate. GR settles it, and in fact, you can make explicit calculation and this is a very important calculation for us later, of the degree to which, so what this means, in fact, is that a light beam traveling near a massive object will, like any massive thing, be deflected so that its straight line motion in empty space will be curved. And I've drawn the curve clumsily, but the net result is that the light beam will be deflected, and the closer to the planet, to the star, the closer to the gravitating source the light beam travels, the more it grazes it, the larger this deflection angle of the light beam will be. The deflection angle is related to the mass and the distance by this formula, which shows you that it's clearly relativistic, but it's to do with light, so that's to be expected. And the effect of this is that if you are studying, if you are observing a star which is lined up with, say, the sun, this is a difficult thing to do, but if you could imagine viewing a star that, if you viewed it correctly, would look as though it were right behind the sun, then that star would actually appear to you, because of the deflection of the light, to be in the wrong part of the sky. So you can measure this deflection. All you need to do is look up at a star right near the sun, but you can't see a star near the sun, except during a total solar eclipse. Fortunately, 3 years after Einstein publishes his paper, there is a total solar eclipse in 1919. This is the middle of World War I. Sir Arthur Eddington, who realizes the significance of Einstein's result, organizes a big expedition to various places in the southern hemisphere where the eclipse will be visible, and they measure, here's a picture from Eddington's original expedition of the total solar eclipse. This is, of course, a negative. You can see the dark being the light chromosphere and corona that they could photograph around the sun, and they do take plates and measure the positions of stars that are very near the sun during the eclipse, and indeed they are deviating from their positions by precisely the amount predicted by Einstein. There were doubts about the precision of the measurement. It's since been reproduced in many ways and at high precision, and this deflection of light by massive objects has become a topic of research in itself. It goes under the name gravitational lensing, and it's a very important tool in modern astronomy. And this famous photo of the Abel cluster is one of the best examples I know of this. This is a Hubble photo. And what we see here in the foreground of the picture, we're looking deep into space. This is the Hubble shot. And these yellow objects are a cluster of galaxies. Now, this weird red-shaped thing over on the right-hand side, I hope you can see it, this is a galaxy which in fact is many light years behind this cluster of galaxies that we're looking at. And the reason this galaxy looks so weird is that the light coming from the galaxy has been deflected by the mass of the galaxy cluster in the foreground, and we see a deformed image of the galaxy spread out. This is not a perfect spherical lens. The distribution of mass here is somewhat interesting, and in fact, this spread out thing, if you look at it carefully in a larger version of the image, you see that it is in fact two distinct images of the same galaxy, both lensed by this, and then once you realize how to look for them, you find more lensed background objects here and here. They show this sort of streakiness like images through bad optics. And so we have in this picture multiple images often of the same background galaxy as seen through the lensing of this galaxy cluster. This has been used by astronomers for many purposes. One is, you have a lens. This means that the light coming from behind this cluster, if things are lined up correctly, will be focused and intensified, and the dimmest, most distant objects we've been able to image have been imaged through gravitational lenses. So you can basically use this as another lens in your telescope. Even more excitingly, this expression that I wrote, theta is 4gm over rc squared, this equation characterizes the deflection of light by the mass that is deflecting it and the distance at which r here is the what I called b in the previous picture, the distance of closest approach of the light beam to the mass. You can imagine adding up the deflections of a given beam of light due to all of the sources of mass in this cluster, and figuring out how light will be deflected, you have here in the image, the lensed image of the galaxy, a lot of information on how different light beams were deflected. You can put them together to learn, in fact, about the lens, about the mass distribution in this cluster. And this is very important. It has been used, for example, to detect exoplanets. When an exoplanet passes in front of its star, the lensing by the planet intensifies the light of the star, and that light curve peak that is characteristic of what's called microlensing events has been used to detect exoplanets, which are otherwise too dim to see. So you're learning about the lens. Another famous example of learning about the lens is, we'll talk in the last week or next week about dark matter. And one of the methods we use to detect dark matter does not produce light in any wavelength and does not interact in any way other than gravitational with anything we know. So we need to measure its gravitational field. One of the ways we measure its gravitational field is by observing the lensing of light, and we can reconstruct the mass distribution, and I'll show you a brilliant example of that next week. So gravitational lensing is a field of study all of its own, and it's a very important tool in astronomy, and it's of course intrinsically relativistic. And then there's the beautiful case of the binary pulsar PSR 1913 plus 16. So this is a pulsar in the constellation Aquila at about 6,400 parsecs from Earth. It's a millisecond pulsar. We didn't get to talk about millisecond pulsars much, but sometimes in binary systems, pulsar neutron stars speed up as they accrete matter from their companion, so that rather than slowing down their period for a while, they speed up. And the period of this particular pulsar is 59 milliseconds. That's a very rapid rotation rate. And we notice when Halsey and Taylor made careful measurements of the pulses from the timing of the pulses from this pulsar, they found that some of the pulses were delayed and some were advanced, and there was a periodic pulse delay with a period of about 8 hours. Turns out, after further study, that the reason for this is that this pulsar is actually a member of a binary system where both members are neutron stars of masses about 1.5 solar masses, and the semi-major axis is 2.8 not astronomical units. That's correct there. The semi-major axis is about 3 solar radii. So you have 2 solar mass objects, but because they're neutron stars, with radii of only 10 kilometers or so, orbiting each other at a radius about 3 times the sun's radius. Moreover, this system is special because the elliptical orbits that these objects follow are very eccentric, and so the distance of nearest approach at periastron, they're only 10% more than a solar radius away from each other. They get very near, and then they move off to about 4.8 or something solar radii at their farthest. And this means we have very relativistic velocities, for sure, when we have 2 solar mass objects at a distance of the solar radius from each other in orbit. And so this is a great lab to study GR. And what do Halsey and Taylor extract from this study of GR in this beautiful lab? Well, first of all, the pulse delay structure is interesting. It exhibits the usual Doppler effect. Pulses are delayed when the pulsar is moving away. Of course, we don't know if both neutron stars are pulsars and one just doesn't happen to aim at us, or maybe the other one does not have jets. We do not know this. But we only see pulses from one of the neutron star. There are other systems that are even richer, where both members are pulsars, but this is the famous first one. And so the pulse display exhibits the Doppler effect. We see that when the pulsar is retreating from us, the pulses are separated by a longer time. But that does not explain all of the pulse delay. I will post a link to a review by Taylor of what it was they did. The calculation is very complicated. You need to take into account many, many effects. But at the end of the day, Doppler effect does not explain everything. It turns out that the pulses are more delayed near periastron than near apastron. When the pulsar is very near its partner, the pulses are delayed by more, and the reason for this is a gravitational redshift. The pulses are delayed because the pulsar is spinning at its accustomed rate in its frame, but as we see it from far away, when it's low down in the bottom floor, close to its partner, there is an additional gravitational redshift, an additional delay in the pulses. Furthermore, they can measure the precession of the perihelion because they can locate where in these 8-hour periods periastron lies, and the perihelion precession agrees completely with GR predictions. So they have a whole bunch of measurements that in this binary pulsar system reproduce brilliantly the predictions of GR. but it gets much better than this. You may recall that a long time ago I talked about quantum mechanics and the problem of stability of atoms, and I said something like, well, if you have a nucleus here and you have an electron that is orbiting it, that's an accelerating charge, and that should radiate electromagnetic radiation, and that would mean it's losing energy, and the electron would spiral down and an atom wouldn't last. How are atoms stable? Well, now that we have a field theory of gravity, you can ask the same question about the Earth orbiting the Sun. The Earth is orbiting the Sun, the mass is accelerating. Remember, that means that there's a ripple in the gravitational field of the Earth-Sun system. That ripple is broadcast out as something called gravitational waves, and those carry off energy. Shouldn't the Earth be spiraling down towards the Sun? Well, yes, but only very slowly. Gravity is a much weaker force than electromagnetism, and therefore the Earth's orbit is spiraling down due to gravity, but that effect is not only negligible, but completely impossible to measure. On the other hand, if you have a system that is accelerating as violently as two neutron stars a solar radius from each other, the emission of gravitational waves carries off a non-trivial fraction of the energy. And what do you expect? Well, you expect the two neutron stars, as they lose energy, to spiral down towards each other, which means, since they're in gravitational orbits, the closer they are, the faster they will orbit. You expect the period, that 7.8 hours, to be decreasing with time. This pulsar was discovered in the 70s and has been studied since. And what you see here is a plot of the decline in the period of this binary pulsar over the past 30 years, plotted against a theoretical prediction from GR of the rate at which the system will lose energy to gravitational waves. And so this is not just evidence for general relativity, as well as a beautiful confirmation of our understanding of the binary pulsar, but it's also telling us that the system is emitting gravitational waves. We'll talk about that in a second, and that gravitational energy travels through space in the form of waves, similar, analogous to electromagnetic waves. What will be the end of this system? Well, as the two neutron stars spiral closer and closer to each other, they're accelerating more and more violently. The motion becomes faster. The rate of energy loss becomes higher. Hence, the decay in the period becomes more and more precipitous. And within as little as 250 million years, they will actually come close enough to violently collide and presumably merge to form, well, a bigger neutron star if most of the material is ejected in the collision, or possibly a black hole, the subject of our next clip. So there's these gravitational waves being emitted. Can we see those? Well, the answer is almost. There are a collection of gravitational wave detectors like this one. This is LIGO, Large Interferometric Gravitational Observatory. And what this is 2 3-mile laser tubes. A gravitational wave passing through will cause the large and well-insulated masses at the tips of these to move by about the size of an atomic nucleus. And because, again, of very sensitive interferometry, this machine is supposed to be able to detect this sort of fluctuation in the relative lengths of the two arms. And it has not detected, as far as I know, gravitational radiation. It's at the end of its calibration run, and sensitivities and noise detection and background reduction are continually being improved, and maybe any day we will hear the discovery of gravitational waves. Now, it won't be from the Halsey-Taylor binary pulsar, because the Halsey-Taylor binary pulsar does not emit nearly intense enough gravitational waves for this detector to detect them, although it is capable of detecting waves. There's a detector in Louisiana, one of the two detectors. This one, I think, is in Washington. And the detector in Louisiana detects waves breaking on the Gulf Coast, which they have to subtract. But it won't be sensitive enough to detect the Halsey-Taylor pulsar. But if something very violent occurs, like the merger of neutron stars, those last 3 orbits before merger are sufficiently violent and sufficiently energetic that enough energy will be emitted in gravitational radiation that we think we will be able to observe such events. This will be the second time in this class that we're talking about non-electromagnetic telescopes. We talked about neutrino astronomy, opening up the field of gravitational wave astronomy, which is what this detector is hoping to do, would give us a whole new window on the universe, and one focused on the most dramatic and cataclysmic events. So we're all hoping that they do detect gravitational waves